In this video, we will show you how a tensile membrane structure is modeled and analyzed. We'll be using NDN membrane software. This is software specifically designed for the engineering of tensile membrane structures. It's the same technology and software used for large projects such as the Millennium Dome in Greenwich, England, and the BC Place Stadium in Vancouver, British Columbia. Today we'll focus on a smaller but quite interesting project. This ferry ship, the Tanger Express, needs a structure to cover passengers on one of its decks. It needs to provide shade and weather protection, but also be attractive and be able to resist the high winds it will be exposed to. The solution of choice is a membrane structure from Dolphin Tensile Awnings of the UK. A tensile membrane structure is very different from a typical awning. In an ordinary awning, the fabric is flat and loose. When it is subjected to wind, it flutters and makes noise. If the wind becomes too strong, the awning must be taken down. The tensile membrane structure is quite different. The fabric is pre-stressed tightly and has a unique double curvature shape. The combination of the pre-stress and the curvature makes it stable and strong. Now let's see how this model will be built. The first thing we need to do is define some basic work line geometry. To save time today, we're going to simply read in a DXF file that contains this geometry. This is the geometry representing half of the structure. What's highlighted in white there is part of the ship that's already existing. This represents the outline of the canopy that we're going to be building. The first step will be to generate the element mesh. We'll generate membrane elements. Segments 12 by 6. And then we'll trace cables around the boundary. Now we need to define our properties. We'll start with pre-stresses. We'll define a pre-stress force in the membrane of 1 kilonewton per meter in all directions. For the cables, we will set a length sag ratio of 14:1 and let the software figure out the appropriate force in each cable. Next, we need to define material and section properties. I will read in some default properties and apply them to the model. Now let me check over my data. We have pre-stress forces in the cables. We're using stainless steel structural strand, assuming 14 millimeter cable for now. The membrane has a pre-stress defined, PVC class 2. That defines our warp orientation and the top versus the bottom. Next, we're going to do the form finding to produce the shape that's in equilibrium with the pre-stress forces we've just defined. We'll go into shape. Now this is a critical part of the design of a tensile membrane structure. We've now produced the shape that's in static equilibrium with the pre-stress forces we've defined. Notice the double curvature in the fabric. This is what keeps it stable under wind. The fabric already has a shape that's suitable to resist the pressures from the wind. It doesn't have to deflect and flutter like an ordinary awning would. Now that we've got the equilibrium shape of the membrane, let's add some of the framing around it. We'll go into our edge post generator, apply a post at the corner. Let's see, at this point maybe it would help us to mirror this into a full model. And I'll delete away the work lines that we no longer need. And again, back to the edge post generator. This time we'll use one cable. Now the unique thing about this edge post generator is it put the post and the cable in the proper position so it's already in equilibrium with the forces. The next step is to define our load cases. Load case 1 will represent pre-stress and dead load. Now let's define some wind load cases. We'll use a base design pressure of 0.584 kPa, which is equivalent to a 60-knot wind. We'll start by blowing the wind in this direction, And to account for the aerodynamics of the shape of the structure, we'll pull coefficients out of a building code library. In this case, ASCE 705. These first few load cases will primarily be downward loads. We'll generate the coefficients, new load case, new wind direction, more coefficients. And now we'll use a different library that produces primarily uplift wind cases. Same wind directions. And load case 8 will represent a live load case. We will use 0.25 kPa live load. Now we have our load cases defined. The next step is to analyze the structure. Notice how the system deflects under each wind load case. It looks like all the load cases have converged, so let's go into the post-processor and look at the results. In the post-processor, we can look at the results of our analysis. Things like deflections under the various load cases, or cable forces, fabric stresses. The other important thing that we do in the post-processor is size our members. Remember, when we built the model, we assumed 14 millimeter stainless for the cables. Now let's see what size we really need based on the analysis. Looks like some of the cables need to be a little bit bigger than 14, but most can be smaller. Now let's size the steel members. We use the British code, set our load factors, and size all the members. What we've learned now is that the member sizes we need are really different than what we assumed when we started. So what we should do is update our model, so our model now contains these new sizes, and rerun the analysis because we have different stiffnesses in the system. And then as a final check, we go back into the post-processor and do a final check of our members. Everything looks like it checks out okay, except a couple of cables. So we'll size these two cables again, and they go up one size. Now let's pattern the structure. We'll go into the pattern environment, select the first area of fabric to pattern. We'll set our fabric width at 1.5 meters. Add a first seam in the middle and tell the software to pattern off in this direction. Same thing on the other side. The third panel. We can review our patterns. This is cutting pattern style, and here they are in an exploded assembly. And next we write our output in the form of a DXF file suitable to read into a wide area cutter. So once again, this is what our completed structure will look like.